افرج تاع تو سكشنز افرج للتو سكشنز. بسم الله الرحمن الرحيم.
هل في فرق بالافرج تبعنا وتبع سكشن ثاني؟
لا نفس الشيء نفس الشيء سيم، لانه ندرس نفس الماده ونفس الكويزز ونفس الامتحانات نفس الشيء. السلام عليكم ورحمه الله شباب. Today we will start a new chapter which is frequency domain analysis of dynamic system. So chapter 9 I'm not sure إذا جتكم الكتب ولا لسه ما جت. Did you get the textbook شباب بالأونلاين textbook or electronic copy? You did not. Okay. inshallah I will do my best يعني to post some problems خلال الويكند هذا for the exam. The exam will include chapter 6. يعني وش نسوي؟ هم قال الجامعه قالوا كذا احنا قلنا كذا، ما لنا دخل في الموضوع هذا. انا اللي علي سويت لكم التمارين المحلوله من الكتاب، يعني I spent some time صورتها وبعثت لكم اياها، هذا اللي نقدر اسويه، اما الكتاب اقدر اصوره كله. في الاكزام خلوني اتكلم بس شويه. chapter we will include chapter 6 electrical system. We will include chapter 7 liquid level system, liquid level, and we will include chapter 8. So 3 chapters. يعني I will do my best inshallah. خلال الويكند I will post some solved problems like the previous one. خلال الويكند احط لكم مسائل. انا حطيت لكم كل النوتس وحطيت لكم تمارين الاي سيريز تاع الكتاب محلوله موجوده. you can see it. والتمارين also اللي موجوده في الكتاب معظم الطلبه زمان كان عندهم السولوشن مانوال، ادري الان اذا عندكم ولا لا. let's talk now about شباب الاكزام. ما ادري يعني it was a straightforward question، بس المشكله في بعض الطلبه ما التزموا في submission of file. submission of the file لازم يسبميت on time. لا تروح اسمه هذه الامرجنسي ابلود. الامرجنسي ابلود راح يخصم عليها درجات، وخصمنا عليها درجه الامرجنسي ابلود. اللي يعني ما اللي كان مسوي زين خصمنا له درجات. خصمنا درجتين على اللي مسوي زين، وخصمنا درجه واحده اللي ما مسوي زين. يعني هذه باش تكون الامور واضحه، ما في شيء نخفيه ولا اي شيء، يعني it should be clear for everyone. So please next time اذا جاء الامتحان في الامتحان الثاني don't go to this this emergency upload، لانه راح تخصم عليك درجات. submit on time وخلاص وانتهى الموضوع. واضح شباب؟ so لا تحط نفسك في مساءله وليش ونصير في بقرة بنو إسرائيل، يعني ما هي وما لونها وتشابه علينا البقر لا، خلاص حط on time الوقت اللي يعني for the exercise وخلاص. يعني لا تحط نفسك لا في مشاكل ولا أي شيء. الآن راح نبدأ الموضوع. اللي عنده سؤال يجيني بعد الليكتشر، نادر تجيني بعد الليكتشر سؤالك. So نبدأ الموضوع هنا. topic about this one you have a system. إذا تتذكروا شباب كنا تكلمنا على any system linear time invariant system. يا شباب هنا الانبوت we have the system في عنا input and في عنا output. كل القصة هنا this is LTI system. The input this time, if you remember, when we talk about chapter 8, we did not talk about sinusoidal input. الآن we will talk about sinusoidal input of the form x of t مثلا equal to a sine omega t. What will be the output? Have the input, this input, what will be the output? And in addition to that, we will look not in time domain, but we will look in the frequency domain. For example, here, if you draw the response of this one for the input, the input will look something like this for time domain. This is t, and this is x of t. بينما في frequency domain, if you look at the frequency domain, you will see just one frequency like this, omega. هنا omega, وهنا one line omega, which is this one. So هنا amplitude, and you will see just one line, which is omega. Hina just one line, omega. This is in frequency domain. So many people, especially in the industry, they look at the frequency of oscillation or the frequency of the operational frequency, and they are interested in operational frequency. Why? To avoid the major problem of vibration that is called resonance. At resonance, people, they want to avoid the resonance point لأنه it causes disasters. So this is what the main topic or the main introduction and the objective of this chapter will be like this. We have an input that is sinusoidal. We will look to the output. What will be the output? And we will go to some details how the vibration is transmitted to some bodies. Maybe some students who took the vibration course, they will be familiar with the terminology here or what we will see here. So this is basically the main points we are going to talk about. And when we finish, we will be able to introduce what is called the sinusoidal transfer function. This is new for you. We will also be able to sketch the frequency plot response in the frequency domain for a given transfer function. And we use these plots for the transfer function to determine the steady state response to a sinusoidal input. Steady state response, as I mentioned to you, Shabab, is the response that will stay with us. We have two responses. This is when you study the me202 differential equation, you call this one the particular solution. Particular solution. In general, the solution X will be composed on two types, on two parts, the homogeneous part and the particular solution. هنا we call the homogeneous, we call it free vibration or free response. That is due to the initial conditions only, initial conditions. This particular is due to the forcing term, due to the force. In the presence of damping, when we have damping, Shabab, I showed you one picture, if you remember, or one small applet, that this term will disappear. This term will disappear with the time, then we have damping. The only response that stays is the particular response, and in this case, we call it the steady state response, XSS, that stands for steady state response. So we will define also the resonant frequency. We will analyze the vibration isolation system and the effects of base motion and rotating imbalance. We will see these things. So rotating imbalance, effects of base motion, the isolation system also. We will use the vibration absorber. We determine the amplitude and phase angle of the output response, and we determine the steady state response to a periodic sinusoidal input. So we will estimate the form of the transfer and its parameter value for a given response data. All this we will cover them, inshallah. I don't know why I got this equation. Now, the frequency response refers to steady state response, as I mentioned to you, to a sinusoidal input. An input f of t is periodic with a period tau if f of t is equal to f tau plus tau. If we have an input like this one, for example, Hina, and you have your responses like this. My handwriting is not good because I did not drink coffee today and I did not take my lunch yet. So inshallah, when I drink them, my handwriting will be nice. So this is the response x of t, Shabab. And let's say this is periodic and it has a period 2 pi. Yani from peak to peak, or let's say from peak to peak, this will be the period. It will be repeating itself. The motion will be repeating itself. Now, this, if you take any point, this one, any point, this is at T1, and you take another point plus the period, this is T2, T1, T2, in such a way, the difference between them is the period. They have all the same yx here. That's why we are writing x of t, f of t is equal to f of t plus tau. Yani they are all the same, having the same value. F of t plus tau, f of t plus 2 tau, f of t plus 3 tau, f of t plus 5 tau, and so on. That's why we call it periodic function with period tau. So all this periodic function. Periodic inputs are commonly found in many applications or in many engineering. The most common, perhaps, is the AC voltage, alternating current voltage, which is sinusoidal. For the common AC frequency, we have 60 hertz. So the period will be 1/60. We have also rotating unbalanced machinery, produces periodic forces on the supporting structure. Internal combustion engines produce periodic torque, and reciprocating pumps also produce hydraulic and pneumatic pressures that are periodic. Frequency response analysis focuses on sinusoidal inputs. We have the input is sinusoidal. So when we say a sinusoidal function of the form A sine omega t, A is the amplitude and omega is the frequency. When we say A sine omega t is exactly like saying A cosine omega t. Then we can obtain sine from cosine just only by using this formula. So this is basically the introduction. And we are seeing here, Shabab, when a linear time invariant system is subject to a sinusoidal input. So this is the input, sinusoidal, characterized by its amplitude and forcing frequencies. This is the amplitude A. Omega here, Shabab, is the frequency. Remember, we have omega. This one is called forced frequency. This is from the machine itself, forced frequency. You remember we studied before, we studied omega n, that is the natural frequency. Omega n, which is usually it is stiffness over mass. This is called the natural frequency. Natural frequency. And today we are seeing the forced frequency. And we have seen also, if you remember, the damped frequency that is equal to omega d is equal to omega n 1 minus zeta squared. We should distinguish between these three frequencies. Forced frequency from the machine itself, natural frequency, this is a property of the system, and the damped frequency when the system is under damped system. When the system is under damped, we talked about the damped frequency. So this response we will contain the following. The input is given by this one. The input is given by A sine omega t. So the output will be something like this. The output will be x sine omega t plus phi. If you look to the input to the output, they have different amplitude. The amplitude of the output is not the same as the amplitude of the input, but they have the same frequency. The same frequency omega, they have the same frequency. And there is also a phase shift between the input and the output. So all we have to do, we know this is the input is given to us. The output will be of the form. All we have to do is to find x and to find phi. لأن omega is the same. To find x, the amplitude of the output, and to find the phase shift between the input and the output. So as we mentioned, Shabab, and this is called the steady state response. Steady state response is sinusoidal and has the same frequency as the input. Okay, Shabab, you remember we said when there is a damping, the natural motion will die, or the motion that is due to the initial conditions will eventually die. Yani it will die out. So this is what we have. Since we know now, Shabab, we know that this is, so we would be interested in finding the output-input amplitude ratio, the amplitude of the output over the amplitude of the input. And we need to know the phase angle between the output and the input. I'll show you now, Shabab, the vibration, how it looks like and how the motion will die out. If you remember, I already, before I showed you this one, but let me just show it to you now here on this website. Just stay with us, don't go away. Please, anyone see the screens? He will tell me, yes, we see it. Now I am trying to share with you the screen. If you see the screen, please let me know.
Yes, we can. Yes.
You see it?
Yeah.
Okay, shukran, Shabab. Now this is what we have, Shabab. You remember, this is the vibration we have. We are having this vibration. This will be the amplitude of the vibration I'm playing here. This one here, we have our mass spring damper system, mx double dash plus bx dot plus kx is equal to a cosine omega t. Here, this is the input now. The right-hand side, this is the input. The input is this one, as you can see. A cosine omega t is the input. It has amplitude A and frequency omega. Now, you will see the motion, how it is moving. I will just change the value. I will change the values here. I will show you the steady state response. Normally, in the presence of damping, I will increase a little bit the damping. I will increase a little bit the ratio here, and I will reduce omega. I will reduce omega, so you will be able to see what will be the time here. Do you distinguish, Shabab, between, I will give you also initial conditions, so you will be able to see it. The initial conditions are from here. This is x dot, and this is x dot, sorry, and this is x, and this is when we have initial conditions. Now, I want you to see the transient response. Shufu, Shabab, this is, I'm showing you the transient response, which is this one. Does everyone see the transient response? It means that this transient response is dying after some time, it will die. See, after sometimes it is, this transient response is due to the input or to the initial conditions. Now, I will show you this, the solution, the total solution. That is the addition of the transient response plus the steady state response. This is the green one. I will show you also the green one solution. This green one solution is the solution due to the forcing term, due to the right-hand side in a cosine omega t. So we have two solutions, the green one due to the forcing term and the blue one, which is the dying solution. The total solution is this. Now, Shabab, if I increase the time, after some time, you will not be able to distinguish the green one from the yellow one. Why? Because because they will be the same, the steady state solution. That's why we call it the steady state solution. It will be exactly the same as the solution, and because the free response will die. Is this clear, Shabab? I will increase maybe the amplitude. You will see it better here. Or I will reduce the amount of damping. See the green one? Is this clear, Shabab, to everyone? Now, Shabab, since we are here, I don't want to move from this page, but because when omega is equal to omega n, this mass spring damper system has its natural frequency, omega n. And this forcing term has its forcing frequency, omega. Now, when omega is equal to omega n, this is what we call resonance. I will make omega is equal to 1 here. I will make omega is equal to 1. I will reduce the time, and I will reduce the amplitude. I'll try to show you, Shabab, the solution, how the solution will move when we have the natural frequency is equal to the frequency itself. I'll reduce the time. I will reduce the amplitude also, so you will be able to see how the amplitude increase with time. I will show you just the solution. When we have omega is equal to omega n, we will have what we call the resonance. Resonance means the amplitude will start increasing with time. The amplitude starts increasing with time, You see the amplitude here, it's increasing with time until the machine breaks. This is, we call it, when we have the natural frequency, and I'm putting m is equal to 1, I'm putting k is equal to 1. So the natural frequency on the left-hand side here is equal to k over m, which is 1. And I am putting also here, omega is equal to 1. So you see now, omega is equal to 1. See what is the frequency, how the amplitude of the vibration is increasing. Is this clear, Shabab? This is what we call resonance, and we don't want our machine to operate at resonance frequency. The resonance will result in high amplitude of vibration, and it will be really a disaster for your machine. It will break the machine. This is what we call resonance. When omega, the natural frequency of the system, omega n is equal to omega, which means the natural frequency of the system is equal to the forcing frequency. Any question, Shabab? Is this clear? Is this clear, Shabab, please? Can you answer the question, please? Is it clear? Okay.
Yes, دكتور.
شوفي شباب, now there is one, if the frequency, the natural frequency is not equal to the forcing frequency, but it is approaching. Yani when it is approaching and you are working on your machine, you have to be careful. You will receive something like this. If you receive this type of response, you have to be careful, and this will tell you that, oh, you have to be careful, your frequency is approaching. If you see something like this, I will increase the amplitude now. Zay samaka, you will see something like the fish, like this. If you see this response, it means your natural frequency is approaching the resonant frequency or the forcing frequency, and you have to be careful. So this one will be like, to pay your attention. You need to pay your attention to what will happen next. Okay, Shabab, so if you receive this one, this is called the beating phenomenon. The beating phenomenon, and this happens when the frequency of oscillations is approaching the natural frequency. Is it clear? واضح شباب? If it is clear, I will go and my slides back. So to our slides back. Thank you for your attention. We will bring our slides back, Shabab. Okay, so we are done. We are here. We are done with this. Now let's take a system, mass spring system with no damping. There is no damping, and this system is subject to a sinusoidal input of the form P of t is equal to P sine omega t, where P is the amplitude of the input and omega is the frequency of the input also. And we are trying to look what will be the response here. The response x of t will be what? When we have a sinusoidal input. So our equation of motion will be simply mx double dot plus kx is equal to P sine omega t. And this is well known for the mechanical system that has mass and then spring system, which can be written in this form: x double dash plus omega square nx is equal to P over m sine omega t. Here, what we did, we just divided by m. When we divide by m here, this term will be 1, and this term will be k over m. You know, k over m is simply omega square n is equal to k over m and p over m. So we obtain this equation where here we have omega n is the natural frequency, as you know, and omega is the forced frequency. So we have omegas. We have omega n, the natural frequency, which is this one, and we have omega, which is the forced frequency. So the total solution of this differential equation, which is a second order ordinary differential equation, it consists of the complementary solution plus the particular solution where we use. Here in system dynamics and control, we call it the homogeneous solution, that is due to the initial conditions and plus the steady state solution or the forced solution that is due to the forcing term here. Now, if we take Laplace transform of both sides for zero initial conditions, we get something like this. S squared plus omega squared n x of s is equal to P over M. Omega over S squared plus omega squared is the Laplace transform of the sine function. Now, this one, as you can see, Shabab, we can write x of s alone, لحاله x of s, if we solve for x of s. If we solve for x of s, we will find P over M. We have two terms, omega plus s squared plus omega squared. This is the right-hand side. And this one will be the left-hand side, which is s squared plus omega squared. Basically, we have four poles, yani two complex conjugate here and two complex conjugate here. We have four poles. So we can write them like this. We can write them A1s plus B1 over s squared plus omega squared, and A2s plus B2 over s squared plus omega square n. So here we have omega square, and we have omega square n. This is to find A, B, A1, B1, A2, B2. I left it as an exercise for you. Solve them, and when you solve them, you will find that this expression of x of s can be written in this form. minus P omega over k minus omega square over 1 omega n. We multiply by omega n and we divide by omega n just to obtain the frequency values. And then P over k minus omega square, omega over s square plus omega square. You see, we have this constant. This is a constant. And omega n over omega s square plus omega square, and this will give you simply a sine term. And this one will be a constant also, and this will give you also a sine term, we are just dividing by omega n. We must, omega over omega n. If you see, omega over omega n is coming here. Omega over omega n is coming here. So this is the solution that is due to the natural frequency, and this is the solution that is due to the forcing term. شوفوا شباب, هنا we have two frequencies. One is vibrating at its natural frequency omega n, that is due to the initial conditions or the free vibration, and the second expression is due to the frequency omega. Frequency omega is the frequency of the input, or the frequency of the force. So the vibration consists of two types. This one, that is at the natural frequency, or the we call it the homogeneous solution. Here we call it homogeneous. And this one, the particular solution or the forced response. So your force will be this term plus this term. When we will have later on, when we will have damping, this term, as you can see, will disappear, and we will have only this one. So for now, we will see, our solution will consist of the complementary solution, which rotate or which vibrate at its natural frequency, plus the particular solution that is vibrating at the forcing frequency. So we have two frequencies, forced frequency and natural frequency. Now, if we look to the denominator only, Shabab, if we look to the denominator, we can call this guy, we can call it A, the whole expression here, we can call it A. And this one, we can call it B, as you can see. So it will be A sine omega nt plus B sine omega nt. So this is the term A, and this is the term B. They have in common K minus M omega squared. We call this guy, we call it denominator, which is K minus M omega squared. We call it the denominator. As you see, Shabab, as omega goes to zero, we will have the term A will be zero. This term will be here 0, and this term will be P times 0 over K. P times 0 over K will be 0. معناته, this will be the amplitude due to the natural frequency is 0. But the amplitude that is due to the forcing term, we will have P over K. You know, this one will be 0, and we will have P over K is the static deflection. The static deflection of the forcing term. So this is what we have when omega is equal to 0 in the beginning. Now, as omega increases from 0, the denominator dn, which is equal to k minus omega squared, becomes small. And the amplitude, this, when omega increases k minus omega squared, when omega increases, the denominator becomes small. If the denominator becomes small, what will happen, since it is in the denominator and it is becoming small, what will happen to A and what will happen to B? Shabab, can you tell me, please? When omega increases from 0, it starts increases. The denominator becomes small. What will happen to the amplitude A and B?
Increases.
They will increase, Shabab. They will increase. Both A and B will increase. So if we can express this one, denominator, we can express it like this. If you want, K minus M omega squared, we take M common, we take M outside. So this one will be K over M minus omega squared. And then we write M. K over M is simply omega N. Now, if we take omega N common, we take it outside. So we'll have 1 over minus omega over omega N. شوفوا شباب هنا, this is in the denominator. This is, of course, the denominator. When omega is equal to omega N, when omega is equal to omega N, the denominator becomes 0. Denominator becomes 0. If the denominator becomes 0, the amplitude A and B become infinity. A, B goes to infinity. This is what we call resonance. This is what we call resonance because the denominator is becoming 0 because omega is equal to omega N and the amplitude of the vibration become infinity. It increases to infinity. This is, we call it the resonance. Resonance result usually in disaster. I'm not sure if I can run this expression from here, but I'll show it to you in my laptop. Let me just bring it from the PowerPoint. Maybe it will come. I hope it will come. This is, of course, many of you maybe are familiar with it. It's called the Tacoma Bridge. It's called the Tacoma Bridge, and maybe you are familiar with it. I'm not sure, but maybe you heard about it when this accident happened in 1940. In 1940, this happened.
When the army move on it and then it falls.
Yeah. I'm not sure if you can see it, but let me just try to bring it. To bring it, I will say, yani share application. I will try to share it, inshallah. Share application. I will bring this one, screen to share. I hope you will see it, but oh, I was not expecting this. Oh no. I will not share this screen, but I will share. I don't know, Shabab, why this one is happening to me. Anyone can solve. انتم ما شاء الله شباب, you are much better than احنا الشياب في الالكترونيكس وفي الانترنت والاشياء هذه. احنا دفة قديمة يعني من الجيل القديم, ما نقدر نتماشى مع التكنولوجيا هذه. We are behind you. انتم share application.
دكتور,
ايوه,
اذا جيت تسوي شير كونتنت
share application.
ايوه, يمديك تختار دكتور ايش اللي بالضبط بسوي له.
لحظه, شو انا ابغى اسوي شير ابلكيشن الان. Do you see my screen?
ديسكتوب بس دكتور, نشوف الديسكتوب.
Desktop, you see my car?
Yes, just your car.
Jaguar. This is not my car, by the way. يعني just لقيتها في الانترنت وعجبتني. I will try to bring share application. I don't know يا أخي why.
We can see the bridge behind the car.
Yeah, but this is not the one I'm trying to show you. Let me just try to bring it to you. It's not coming. I don't know. Now I want you to see the PowerPoint presentation. You see PowerPoint? Oh. See the story here, the story. Shabab, please let me know if you are seeing something that says the story of the camera picture, you know.
Yeah, it's clear.
It's a little bit slow. I don't know. Maybe the internet is not clear. This one is the Tacoma Bridge. As you can see, there is a river here. And this is not the Tacoma, the bridge itself, but it will come. This Tacoma Bridge starts vibrating in May 1940. It starts vibrating. This is when they are building the bridge. Now they are building the bridge. It starts vibrating, and the wind also starts vibrating. And this is the grand opening in July 1, 1940. This is the opening ceremony when they opened the bridge. At that time, Shabab, the bridge, it started vibrating. The wind also starts vibrating, and when the vibration of the wind reach exactly the same vibration of the bridge start vibrating in swinging, and it starts vibrating. You see now, maybe the bridge, you can see it, it's swinging at its natural frequency, and
as if it is paper.
The amplitude started increasing until the bridge collapsed. This is in 1940. And I was not born at that time, don't worry. Maybe also, I'm not sure fathers were born at that time.
Doctor, this is concrete?
Yes, it is concrete and steel, of course. Steel and concrete.
It is like paper now because of the frequency, because of the
it is weird.
See the vibration was, yeah. Now the guy who is inside, he wants to rescue a dog. The dog was in the car. I want you to see the guy is still running to the car to rescue the dog, this guy. Now he felt the danger and he is coming back.
والله لا اهج يا دكتور بلا كلب بلا هم بهرب ايش اقدر اسوي
Now it will take maybe 1 or 4 minutes. You will see the bridge how it collapsed. This was in 1940. 1940. See the collapse, شباب. So في الاندستري شباب همهم الوحيد is to avoid the resonant frequency. This is the most dangerous point, is to avoid the resonant frequency. And I have showed you شباب the resonance, how it is making the amplitude high. Either you have seen the film now, or in the lectures. You've seen the lectures. I will end the slide شباب. Now I think time is over. I'll just
دكتور طلع يا شباب.
من مزعل الدكتور؟ مين مزعل الدكتور يا شباب؟
لما القطة حقتك شفت ايش سوات؟
اوف علي البشير بيجي تهاوش الحين يقول من زعل الدكتور. طيب يا شباب انا بعلمكم الدرس اليوم.
والله كنت قاعد على الجوال يا رائد وشفت سكوت فجأة
نتكلم عن انه اذا كان في الريزونانس
just got disconnected.
اهلا دكتور.
Sorry, يعني I'm not sure what happened. هنا الانترنت from time to time is not really good either at home or in the.
عليك يا دكتور. توليت زمام الشرح عليك.
شباب can you please give me some time. حسين القحطاني موجود؟
ايوه موجود يا دكتور.
موجود بعد الحصة. الله خليك ابغى اكلمك بعد الحصة.
طيب ان شاء الله.
خليني اخذ الاتندنس ناو بليز شباب if you don't mind. علوة منير ما شفتك المرة الماضية. what happened الحصة الماضية؟ فيصل دي قلبي. سلامات ان شاء الله.
موجود يا دكتور.
ايوه دي قلبي فيصل. مسعود عبد العزيز. الملا ماجد يا ماجد. القحطاني حسين.
ايوه دكتور.
محمدي عبد العزيز المحمدي. القحطاني عبد الكريم. الشهري علي. الرميح هاني. القرني علي. زهراني فارس. الحمدان عبد العزيز.
يس.
الشريدة محمد.